Okay, let's make a start. Looks like I got drew the short straw this evening with the last session of the day. Everyone wants to go and drink beer, so we'll go quick. So this is me. I'm Matt Jarvis. I'm Director of Community at Mesosphere. For those of you who aren't familiar with Mesosphere, we build cluster orchestration software based on Apache Mesos. I've been around open source software for a long time, and worked on ops and developing of distributed systems. So, for those of you who aren't Star Trek fans, this is a still from one of the most famous episodes of the original series, where the crew of the Enterprise encounter the Tribbles, these furry round things. This is an alien species that reproduce incredibly quickly. And you might ask, what has this got to do with Kubernetes? Kubernetes cluster growth has rapidly become one of the big pain points for organizations using Kubernetes, and coining the phrase Kubesprawl. And sprawling isn't just about increasing in size, it also implies things that are unplanned and uncontrolled. And the emerging pattern amongst enterprises is to have multiple Kubernetes clusters, some figures showing as high as an average of 15 clusters per enterprise. And when we combine that with 70 plus different ways of deploying Kubernetes, and a large proportion of these clusters not being managed by a central IT organization, and that most of them are pretty small, then we can fairly easily see what happens with complexity and with efficiency. So the original idea behind Kubernetes and really behind all cluster orchestration systems was to provide a single pool of resources, abstracting away all of your underlying infrastructure. But as we've just seen, this hasn't happened in reality. So why is that? And there's obviously going to be a variety of reasons across organizations, but some of the more common ones are these. The change to this kind of container-based ecosystem with all the rapid development and deployment that comes along with that has somewhat upset the apple cart in the more traditional enterprise security world. And having a shared kernel is perceived as a softer multi-tenancy model than in the hypervisor-based virtual machine world. And so this has led to the cluster itself being considered the hard boundary from a security perspective. And container-driven development has also empowered development teams to set up their own deployment infrastructure. And these have tended to exist outside of those control boundaries of internal infrastructure teams. And this can be because of frustration with pace within organizations. And in many enterprises, there can be a disconnect of speed between development teams and other teams who may have more rigorous control mechanisms imposed on them. And then thirdly, there can be this perception about scaling. Kubernetes is a monolithic scheduler, meaning it controls both resource allocation, i.e. how many CPUs and how much RAM are allocated to a particular process, as well as workload placement. Where does a particular container live? And what are the rules involved in placing it? And because monolithic schedulers have to know all the things, it's typically been seen in computer science as less able to scale to very large node sizes in clusters and workloads. And it's important to note that these may or may not actually be true, but in any organization, perception is reality. So to some extent, it doesn't actually matter. So we've got a bunch of clusters, and they're increasing in size a bit. Well, what does it matter? Well, individual teams will have individual methods of deployment. Even if we standardize, there may be subtle differences which over time could eventually create issues. Engineers with ingrained knowledge move on, and code is fundamentally brittle. The operational overhead of clusters also isn't just about deployment. We have to take into account the full lifecycle. Outside of cloud platforms, many tools only handle deployment. But for distributed systems, this is only a small part of the complexity. How we handle upgrades, how we handle failure scenarios, how we handle scaling are all highly complex operations. And even more importantly, we have a significant cost problem. Allocating physical or virtual machines to each kubelet has a cost. Even in a cloud platform, you're being billed for the CPU and memory allocation, not how much you actually use it. And for on-prem, you're clearly going to be paying for power and cooling of those machines. So fundamentally, from a resource allocation standpoint, this has become a static partitioning problem. We physically allocate resources to each of our clusters based on a situation at a particular point in time. And static partitioning has long been recognized as a major issue as applications become larger and more distributed, because it's generally pretty inefficient in terms of resource utilization. We end up over-provisioning to deal with peaks and troughs, or to deal with potential failure scenarios. Now, you could argue that in cloud platforms, you can scale up and down, and that's certainly true, but that relies on teams taking advantage of those features, understanding capacity provisioning for different failure domains, tracking resource metrics effectively, and building automation to handle all of that. And it also relies on being homogeneously in a particular cloud platform to start with. And none of those things are necessarily prevalent right now. Now, all container orchestration systems are built, at least partially, so that we could handle the problem of static partitioning at the application level. So it's kind of ironic that we now end up moving the same problem into the infrastructure space. So one solution to the general static partitioning problem is Apache Mesos. You can think of Mesos as a distributed kernel. Much like the Linux kernel, Mesos is responsible for low-level task scheduling. But you can also think of Mesos as a distributed system for running other distributed systems. Mesos is massively scalable. It's battle-hardened in production to tens of thousands of nodes. The biggest Mesos clusters these days are in the region of 70 to 80,000 nodes in a single cluster. And it's in production at some of the world's biggest internet services. So if you've used Twitter, if you've used Netflix, if you've used Uber, then at some point your interaction with those services has passed through Mesos. And in fact, Mesos and Kubernetes share a common lineage in that Mesos was originally conceived as an open source version of the same kinds of massively scalable schedulers that had already been built inside Google and Facebook. And if you view Borg as the progenitor of Kubernetes, then you can see that the relationship there. And Twitter were one of the first major adopters of Mesos, and for those of you who are old enough, you may remember this graphic, the fail whale. This used to go on Twitter's website whenever the service went down. And in the early days of their scaling curve, this was a very common issue. And Twitter then switched their infrastructure over to use Mesos, and that's one of the big reasons why you don't see this anymore. So let's take a look at the architecture of a Mesos cluster to understand how it is one solution to that static partitioning problem and kind of what makes it different to Kubernetes. So fundamentally, in a Mesos cluster, we have a bunch of masters, only one of which is in charge at any one time, and a bunch of agents, which are effectively your physical or virtual machines. And we also have a zookeeper cluster, whose job it is to maintain, to manage leader elections when a particular master fails. The main difference between Mesos and all other cluster orchestrators is the concept of two-level scheduling. Mesos doesn't actually care about workload placement. All it cares about is resource allocation. It offers up whatever resources the agents below it offer up, and applications, distributed applications running on top of Mesos decide whether they're going to take those resource offers. Applications which run on Mesos are generally called frameworks, and they consist of a scheduler and an executor which runs on each agent. It's the framework schedulers that decide on the workload placement based on accepting or refusing offers from the master. And this is because they're the ones that are best placed to understand what the requirements are for their particular application, what the data locality requirements are, where things needed to be placed in relation to each other. So ultimately, application logic is maintained in that second level scheduler, separating out those concerns. And this non-monolithic scheduler model has proven to be much more scalable than trying to hold everything in a single scheduler. And the other important thing to note about Mesos is that everything is a container. And that doesn't necessarily mean Docker containers. Mesos actually predates Docker. It has its own containerizer that understands the levers to configure in the Linux kernel to isolate processes with C groups and namespaces. But it also understands the Docker image format, understands about Docker registries and the plumbing that needs to happen there. And you can also use Docker as the containerizer itself. So what we get when we run Mesos at the bottom layer is we move from having our frameworks kind of siloized with resources statically allocated to each of them into a model where our workloads are now multiplexed on the same machines. And what that means is we get much higher resource utilization. As I said earlier, Mesos is fairly low level in its concerns, and you actually need to stack a bunch of stuff around it in a production environment. Most of those big web scale users have built their own in-house management systems to do that, which is where DCOS comes in. DCOS is an open source project primarily developed by Mesosphere, which provides all the additional functionality that you need to run Mesos in production. Load balancing, service discovery, operations tooling, and a built-in catalog of pre-configured frameworks. You could think of DCOS like a distribution of Mesos. And so what that looks like from an architecture perspective is Mesos at the bottom layer, together with container orchestration provided by either Kubernetes or by Mesos' native orchestrator Marathon. It's got a UI, a CLI, and an API, together with all the tooling to provide all the operations and monitoring functionality. And then at the top layer, we have all those frameworks that you can run on top of Mesos. And DCOS can run on pretty much anything, public clouds, VMs, bare metal. The idea of it is basically giving you that flexibility of public cloud, but on infrastructure that you control. So at Mesosphere, we start to think about the challenges of building high-density Kubernetes, where we could leverage Mesos to effectively bin pack multiple Kubernetes clusters on top of the same underlying infrastructure, and at the same time simplifying the operational lifecycle management issues of running multiple Kubernetes clusters. What do Mesos and DCOS give us for running Kubernetes and trying to solve that Kubesprawl problem? Well, as I said earlier, frameworks are not package installers. Whilst they orchestrate deployment, they also orchestrate the full life cycle of the application, handling upgrades, downgrades, scaling, failure scenarios, and so on. And the scheduler's job is also to keep the defined state of the application at all times. So if parts of the deployment fail, they'll be respawned somewhere else in the cluster. And in this way, DCOS and Mesos effectively do the same thing for Kubernetes clusters that Kubernetes does for the applications that it's running. So we can look at the DCOS CLI to see what lifecycle phases a particular scheduler knows about. In this case, this is the Kubernetes scheduler running on DCOS. And it knows about deployment, knows about node replacement, knows about recovery, updates, and uninstallation. And if we dig a little deeper into a particular scheduler plan, we can see the strategy and kind of operational best practice that's embedded in that code. In this case, we're looking at the execution of a deployment plan. And the scheduler is showing that it knows it has to bring up the etcd cluster serially to make sure that the nodes synchronize, but other operations it's able to parallelize, for example, bringing up the API servers. This is clearly much longer than I could fit on the screen here, so it's been snipped for brevity. But this operational logic applies to upgrades and scaling too. The scheduler knows which operations have to happen in which order, when it has to wait for other activity to complete, and so on. So running on Mesos using a scheduler can simplify the operational workload of deploying and managing distributed systems, but what additional problems do we need to solve before we can multiplex multiple Kubernetes clusters on the same machines? Most importantly, we don't want to fork Kubernetes. We want to run unmodified upstream Kubernetes code so all the standard integrations work, and so it's no different an experience for an end user. And we basically want as vanilla experience as possible. When we deploy Kubernetes into our environment, we define a kube node as the single addressable entity which contains the kubelet, the kube proxy, the container runtime, and all the associated applications inside a Mesos container. And we allocate RAM and CPU to that entity, to that kube node entity. So the first and most obvious problem that we've got here is that the kubelet and the container runtime, to some extent, expect to have all the resources on the machine. That's going to affect us in a couple of different dimensions. But let's look at the obvious one to start with, which is that we need to tell the kubelet only to use a certain amount of the host's resources, i.e. the amount that we've configured for the container containing our kube node, and not the whole, all the resources that are on the agent. This is actually fairly easily solved, as Kubernetes provides us with some levers we can use to configure this in these flags for kube reserved and system reserved. And in our Kubernetes framework config, we have two configuration flags for the kube node resources, reserved and allocatable, which define how much to reserve for the kubelet and how much to allocate for pods. And by using a combination of these, we can effectively trick the kubelet into having the right amount of CPU and RAM allocated for pods. And the kubelet would normally work out how much to allocate for pods by subtracting kube reserved and system reserved from the total available on the host. And it reads this from proc CPU info and proc mem info on startup. And in our case, that would clearly give us the total available on the agent because we're running it in a container. So in our case, we need to set system reserved by working the other way around, subtracting the amount we configured in allocatable from the total available minus the reserved. So as an example, if we want our kube node to have 3 gigabytes allocated to it, 2 gigabytes of which is allocatable to pods, and 1 gig is reserved for the kubelet, the container runtime, etc. When we calculate system reserved, we subtract those from the total available resource, then start the kubelet with kube reserved set to 1 gigabyte and system reserved set to 17 gigabytes. And although subsequent kube nodes deployed to this agent will be unaware of the other kube nodes that are running on that host, and they'll continue to see that total amount of resources available on the node, and this won't actually matter because as we add more kube nodes, eventually we get to the point where Mesos won't actually offer any more resources from that agent once all the resources are allocated. However, we still do have a problem around memory usage, and in order to understand that, let's have a quick refresh on how process isolation works. In containers, processes are resource limited and accounted for by using control groups, C groups. This is a feature of the Linux kernel. They're hierarchical, so processes inherit the parent C group limits. And in our cases, pods spawned by a kubelet inherit the kubelet resource limits. And when we set limits for a C group, and the C group uses more memory than that, and the kernel will kill processes within that C group to bring it back under the limits. C groups can be accessed via the procfs API, which is usually mounted at sysfs C groups. And the kubelet uses CAdvisor to get the memory usage of all of its pods. CAdvisor is code originated at Google to understand resource usage and performance of running containers. And because the kubelet assumes it has sole control of the machine that it's running on, CAdvisor looks at sysfs C group memory to read the memory usage of the C group. And normally, the kubelet will get those figures, compare them to the total memory available, which it read at startup from proc.meminfo. And if it detects memory pressure, it will signal to the control plane and then automatically evict pods from that particular node to get things back under the limits. So in this example, we've got 3 pods using 3 gig each, plus Docker and the kubelet itself are using 1.5 gig. And so the kubelet reports memory pressure, evicts a pod, keeps things under the limits. In our case, we had 2 problems with that approach. The first one is that Mesos had a different C group hierarchy because everything is effectively a container under the resource limits assigned to Mesos in the first place. In Mesos, each task is assigned a C group under the Mesos parent group. In this case, UUID is the kube node, and all of the pods are assigned to a C group in kube pods under that hierarchy. So when CAdvisor reads sysfs C group memory usage in bytes, it's actually reading the resources of the agent under the root C group. So the solution to that was actually a change in Mesos to implement per container C groups, where inside a container, we bind mount over sysfs C group with the sysmesos UUID. And now when CAdvisor goes to read that, it's reading the usage from the container C group. But this isn't actually quite enough to solve the memory pressure issue. You'll remember that the kubelet reads the total RAM available on the machine at startup, which is a pretty safe assumption since memory doesn't normally change in operation. What that means, though, is that the kubelet thinks it's running in 20 gig of RAM in this example, when actually it's containerized inside 10 gig allocated from Mesos. And whilst the memory usage that CAdvisor is reporting for the C group is now correct, when the kubelet calculates the overall memory usage, it doesn't take into account the Mesos limit. So for each pod launched, you've got some overhead there when managing Docker containers, as Docker spawns an extra process, the containerd shim process to manage the lifecycle of the container. And each Kubernetes pod also spawns the pause container. And in effect, you're launching 2 processes for each Kubernetes pod, and they're all going to consume some resources there. This could lead to the memory usage of the kube node becoming more than 10 gig. And at that point, the kernel will start killing things, probably the kubelet, and we'll be in a very bad scenario there. So we have a similar problem with disk usage. There's currently no C group to limit disk usage. So CAdvisor looks at the root disk usage using statfs. And the kubelet responds, as with RAM pressure, by evicting pods. And in our case, this won't work since the root is the whole disk of the agent. So our first iteration solution to that is to use a sidecar process. So we have this kubelet resource watchdog, which monitors the pod's container runtime and kubelet resource usage. And it also knows the resource limits that have been allocated to the top-level container by Mesos. So if it detects pressure, it will basically do what the kubelet would do, impersonate the kubelet, signal to the control plane that pressure has been detected, and then evict pods. And this approach isn't absolutely perfect, since the kubelet and the watchdog can effectively be reporting conflicting information to the control plane, but for now it works in practice. So the final piece of the puzzle is the networking stack. The aim here really is to provide network isolation between clusters with no impact on native Mesos workloads, which may also be running on our cluster. And as with our other efforts, we want to avoid forks, and we want to allow the use of off-the-shelf CNI plugins. And the aim here really was to be reasonably performant for the general use case. So not necessarily to solve for very low latency, very high throughput networking configurations. So we looked at a bunch of different approaches here. We need to make sure that we achieve the network separation and that we make sure that pods on different agents can communicate with each other. So we looked at solutions that use encapsulated overlays, in this case VXLAN, which is supported natively in DCOS, and rooted SDN type solutions using Calico. And we built proof of concepts for a range of different configurations. And there were a variety of things that worked and didn't work, as is usual with these things. Because of all the different layers involved, things can get a little bit squirrely. So let's take a look at a couple of things that just didn't work for this particular use case. And this first example is using overlays, both kube nodes and pods directly in the host network namespace. This will all work since effectively we have layer 2 adjacency between everything. But if we want to run multiple Kubernetes clusters, this is very rapidly going to get operationally complex. And it's not got very clear separation since all of our clusters are basically going to be in the same network namespace. So the second example is using Calico with both kube nodes and pods connected directly to the host network. This isn't a great solution anyway, because again, it pollutes the host network namespace. Excuse me, but let's look at why it doesn't work. Each workload, in this case, the kube nodes and the pods, has the other end of a veth pair in the host network namespace. And we can see the sample host routing table in this diagram. So there's a /32 route for each workload via the Calico veth interface, those cal1 and cal2s, and a /16 route for the other agents via the tunnel interface. So pod 1 can directly interact with pod 2 without any issue. But when pod 1 wants to connect with pod 2 via a service address, the packet has to go through the kube node, the kube proxy, to get natted. And in the routing table there, we can see that we've got a route for that service CIDR via 9.0.1.2. But once that packet hits the host network, the host doesn't have a route to the 10.100 address range. So ARP packets just get dropped in the host network. So there's another example which has issues. In this case, we connected the pods directly to the kube node interface via a bridge in the kube node container. And here we can see that pods that aren't on the same agent can't actually communicate with each other at all because Calico just doesn't know they exist. And there were solutions where this could work. For example, we could have had 2 interfaces in both our kube nodes and pods. But again, this is going to get pretty complex. We need to have a custom CNI plugin to create these interfaces and bridges. And it's going to get really unwieldy for multiple Kubernetes clusters. And we probably also run the risk of network collision here, since we're just operating in the host network namespace. So the final solution we chose was this one, what we call overlay on overlay. So at the bottom layer, each cluster is separated from the host network by an overlay network, in this case, VXLAN. So we have layer 2 separation of all traffic on the wire. And within the Kubernetes cluster, we run Calico with all our pods connected to the network inside the kube node. And that gives us both the separation between clusters and the connectivity between pods running on different agents across our DCOS cluster. And so in terms of performance, there's clearly going to be some overhead in running overlays and SDN solutions against bare metal. As I said before, our aim was to solve for the reasonably performant general use case. And here we can see the throughput of pod-to-pod traffic, i.e. without any SDN involved, versus the throughput of agent-to-agent traffic. And as payload sizes get bigger, the impact does get larger. But overall, it's within our acceptance boundaries. And it's a similar story for latency. So hopefully, I should be able to show you. Let's just. Here's one I built earlier, hopefully. Where are we? So this is a DCOS cluster I've got running in Amazon. This has 10 public agents, and on top of this, we're running just four Kubernetes clusters packed on top of each other. You can see from the underlying infrastructure, we get a pretty high node utilization in the underlying virtual machines. And there's really no difference to interacting with Kubernetes in this context than when you've deployed. Let's just exit that. So you can see I can use kubectl to connect to all of those different Kubernetes clusters. And I should also be able to view the, I've already got that there. And I can view the Kubernetes dashboards as well for each of those just by switching my context. So that is pretty much it. If you're interested in trying out, let's just put that back to there. If you're interested in trying out any of this stuff, there's a bunch of different ways that you can try out DCOS. We have automation templates for most of the public cloud platforms, and you can run it locally on, in Docker and in Vagrant. And we have a big community that you can explore and find our website at dcos.io, our Slack channel at chat.dcos.io, and we've got a bunch of code and demos and examples and stuff in GitHub. Thank you very much. I think we've probably got time for a couple of quick questions. Thank you very much then, folks.